All right, hello everyone. Next to the last lesson in the regular textbook here. So far in this chapter, or near the where we're at here, we've been talking about power series and taking a function and writing as a power series. That's what we did last section, but we kind of got a little convoluted. So today's lesson is how do we write a function as a power series? So the last section we're kind of bouncing back and forth and doing some word stuff with. So we're going to just show you how to do that. So these are called either McLauirin series or Taylor series. McLauirin was the first guy to figure this out, and then Taylor came on. McLauirin did it specifically for one value, and then Taylor came along and did it generally. So McLauirin kind of got swept by the side. We try to still use his name a little bit, but sometimes it disappears a little bit. So here are the two questions we're going to answer today. Actually, one question we're going to answer that we'll kind of ignore. The idea is if a function has a power series representation, okay, and there's two ways to write power series. We've seen both of these. The McLauirin series is with the c being 0. So you just have a to the n, x to the n. The Taylor series has c being some other constant other than 0. So McLauirin is specifically for c equals 0. So if a function really has a power series, how do we do it? How do we find that a sub n? That's the goal of today, basically, is how to find that a sub n. Second question is, what conditions are sufficient to show that it has a power series? We're not going to delve into that at all right now. Probably won't much in this course at all. It's for later on a little bit. Here's what McLauirin came up with. He said he figured this out. I'm not really sure how. It's pretty darn smart, that's for sure. That if a function has a power series representation, we're going to need to use its derivatives to find that power series. So if a function, this just starts off by saying if a function has a power series representation with some radius of convergence, and the derivatives exist, so this just says the derivatives exist for every integer, for every derivative, this is how you find a power series. You take the function and you put 0 in. Then you take the first derivative and you put 0 in and you multiply it by x to the first. Then you take the second derivative, that's a little small, sorry. Then you take the second derivative, plug in 0, multiply it by x squared and divide it by 2 factorial. And you continue this pattern on and on indefinitely. So it's the nth derivative. So what you see right here is the nth derivative evaluated at 0. So you're going to find each derivative, plug in 0. Depending on which derivative you're finding, you're going to multiply it by x to the n over n factorial. So if you're like finding the 7th derivative, you just find the 7th derivative, plug in 0, multiply it by x to the 7th over 7 factorial. We're going to do two things. One is we're going to generalize. So like we're going to try to find a pattern for these things. The other times we might just find the first 3 terms or something like that. Sometimes the patterns are really hard to find, so we don't even bother with that. Taylor then came along and he went one step further, basically, and said, how are we going to do it if that c is in there, if it's not 0? And it's basically the same idea. But in this case, instead of plugging in the 0, we're going to plug in whatever the c is. Seems logical, right? And before the c was 0, we plug that in. And then we're going to, instead of multiplying it by x, or x to the second over 2 factorial, we're going to multiply it by x minus c, because we need this term in there. So that's it. I'm just going to do a bunch of examples. We're going to do some more study with it in the last section, like why it's useful, what we can do with it. Right now, we're just going to show you some examples of how to do it. It's kind of a long process. We're going to start with an easy one. We've already done the e to the x. The first couple are kind of easy. I'm going to come down here, actually, where there's a little more space. Here we go. So I'm going to kind of walk you through the process. So this is my function, and we're trying to find the power series. We know that this power series is x to the n over n factorial, right? We did this the other day. But we're going to show you how to get this using this formula. So I do this with a little chart. It's going to be really easy for this problem because of the nature of the derivative. So what I start with is an n. So n is 0, 1, 2, 3, ... Ultimately, we're going to try to generalize and go with what n is, okay? And then I do derivatives here. So this is like the nth derivative, okay? So the 0 derivative is kind of like the function, right? Remember the first thing we do, if you go back to this, sorry, the first thing we do right here, right, is plug 0 into the function. We have to plug 0 into all of the derivatives, including the function. So back to this. So the first is just e to the x. Now I'm just going to start taking derivatives. Granted, this is a pretty easy one. I see the pattern. Anyone else see the pattern? All right, so they're going to get a little more complicated than this. Then what we're going to do is we're going to take that derivative, we're going to plug in 0, right? 1, 1, 1, 1. We look for the pattern. In this case, very easy. It's always 1. Okay, and then what we do is, remember, this has to get multiplied by x to the n over n factorial. Okay, so I'm going to take that 1 and multiply it by x to the n over n factorial, which is x to the 0 over 0 factorial. So that's just 1. So it's 1. This one gets multiplied by x. This one gets multiplied by x squared over 2 factorial. This one by x cubed over 3 factorial. And this one by x to the n over n factorial. This is ultimately what we're looking for down here, right? It's the pattern. So the power series for e to the x is n equals 0 to infinity of x to the n over n factorial. Pretty simple, right? So that's the process. Finding the pattern can be the hardest thing here. Some of these derivatives get really complicated. You know, you can't really do, I can't just make one up, because if I just make one up, there might not be a nice pattern, right? So that being said, yeah, I'm just going to go with some that we already know, I guess, and then I'll give you a new one. So I'll do one more here. I think we've done 1 over 1 plus x before, right? So we're going to start with this one. So the same process, 0, 1, 2, 3, 4, 5. I don't need that many. I just need to do it until I see a pattern, right? And then n, the nth derivative. So 1 over 1 plus x. The first derivative is negative 1 over 1 plus x squared. The next derivative, it's just a power rule, right? So it's like 1 plus x to the negative 2. So I'm going to drop that negative 2, and it's going to be 2 over 1 plus x cubed. Now I'm going to drop that negative 3. It's going to be negative 6 over 1 plus x to the 4th. All right. So I'm just going to kind of keep on. Maybe you can see the pattern. There's a negative 1 floating around to the n. It's alternating. All right. Negative 1 to the 0 is 1, so the first term is positive. And then we have a factorial on the top. This is actually 0 factorial. This is 1 factorial. This is 2 factorial. This is 3 factorial. So it's n factorial. So there's an n factorial on the top. All right. And then on the bottom, we have this 1 plus x to the, it's n plus 1, right? The first one had a power of 1, the power of 1 here, power of 2 here, power of 3 here, power of 4 here. So 1 plus x to the n plus 1. But we're going to plug that in anyway. So watch. What we're going to do next is we're going to plug in the 0, right? If it was a McLaurin, a Taylor series, we would plug in whatever number it is. We'll let you play around with those on the homework. So I plug in the 0. I get 1, negative 1, 2, negative 6. The bottom is just always going to be 1, right? So really what I have here is the negative 1 to the n. This is just going to be 1, so it's gone. So it's n factorial, right? You don't really have to find these. I just like to do it. Really what you have to find is this one here, right? So sometimes it's easier to see it once you're done. And now we're going to multiply it by x to the n over n factorial. So this one just gets multiplied by 1. This one gets multiplied by x over 1. This one gets multiplied by x squared over 2 factorial. X cubed over 3 factorial. So notice these are going to cancel, yeah? Because that is 3 factorial. So when I'm all said and done, I have the alternating piece. The n factorials cancel, right, on both of them. So we just have x to the n, which is what we knew from the first day we did this, right? Negative 1 to the n, x to the n for 1 over 1 plus x. It's that geometric series with a common ratio of negative 1 that we did. All righty. I'm going to do one more example because I think we're going to need it for the homework. Maybe 2 real quick, sine and cosine, just because I think you need them for the homework. The rest are kind of up to you. Just follow the pattern, look for a generalization. Sometimes they won't only ask you for the first 3 terms. If they only ask you for the first 3 terms, or 4, however many, it would just be that, right? You wouldn't have to do anything more than that. So let's do sine x. So let me kind of whip through this quickly. hopefully you guys know what these things are now. We're going to 0, 1, 2, 3, 4, 5, dot, dot, dot. The function is sine x. The derivative is cosine x, negative sine x, negative cosine x, sine x, and so on. Something a little different is going to happen here. Don't worry about generalizing until the end. Now we're going to plug in 0. So we get 0, 1, 0, negative 1, 0, 1, so on. So notice we're losing every other term, sorry. And then the last thing is to multiply by x to the n over n factorial. So this first one gets multiplied by x to the 0 over 0 factorial, which just is 1, but 0 times 1 is 0. So this gets multiplied by x. This gets multiplied by x squared over 2 factorial, but it's going to be a 0. This gets multiplied by x cubed over 3 factorial, 0, x to the 5th over 5 factorial, and so on. So now you can see the pattern. It's actually an x minus x cubed over 3 plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. This is sine x. We just need to generalize that. So what I see are the odd powers, yeah? I see the odd powers. So we're going to put in a negative 1 to the n. The first term is positive. Negative 1 to the 0 is 1. And then we have an x to an odd power. And notice also that the power and the factorial are the same, right? So the power of x is the odd power. So when you plug in 1, you get out. When you plug in 0, you get out 1. You plug in 1, you get out 3. You plug in 2, you get out 5. So that's actually 2n plus 1. You can check it if you don't believe me. This is sometimes the hardest part of these problems is finding that number. And then we got a 2n plus 1 factorial. I'm just going to give you the cosine x and then be done. You can check it. It might be a good idea. Fun for you to check it. You're going to have to do a couple of these on your own. Cosine x, the same thing happens. Every other term drops out, but we're left with the even ones. So we wind up with cosine x being, that should have been an n there, sorry. N equals 0 to infinity. We got the negative 1 to the n, but this time we just have x to the 2n over 2n factorial. So remember, whenever you have these, you can, so if someone asks you to do sine 2x, let's say, you have two choices. You can go through that whole process I just did. It won't be the end of the world, but it'd be a little more complicated than what you could do. You could use this pre-existing series, remember, and just plug that 2x in for x, you'd be done. It'd be like one step. So sine 2x equals summation negative 1 to the n, 2x to the 2n plus 1 over 2n plus 1 factorial. That's all you got to do. So once you have a pre-existing one, you can continue to use them. Or let's say I didn't even have the pre-existing one. The derivatives of sine x are simpler than the derivative of sine 2x, right? So you could simplify it, find the simpler one, and then plug in afterwards, kind of your choice. It's going to take some practice for sure. It's a little long process, but do your best, and we'll go over some of them in class.